It's great to be back in Hyderabad. I'm probably the least qualified person in this session. My main qualification for giving this talk is that I happen to be present while TIFR Archives, Ananya Dasgupta of TIFR Archives was conducting an oral history interview of Sudarshan, and that in many people's eyes has made me an expert on Sudarshan. So here goes. Okay. My talk will have some degree of overlap with Debajyoti's talk, and then we'll run into reminiscences from his oral history archive. But in order to understand what the reminiscences are about, I have to go through the physics. Debajyoti has talked about some, we've already heard about some of this previously, but this is going to be a bit different, slightly different. Okay, so all of you know that some nuclei undergo beta decays. For instance, if you take boron 12, which has 5 protons and 7 neutrons, it undergoes a beta decay to carbon 12, emitting an electron and an electron neutrino. Sort of conversely, nitrogen 12, which is 7 protons and 5 neutrons, undergoes a beta decay to carbon 12, emitting a positron and an electron neutrino. Now, what is the physics that underlies these reactions? In a sort of seminal paper, which was duly rejected by Nature in 1933, Fermi proposed that all these beta decay reactions have the same underlying mechanism, that they're caused by the decay of either a neutron into a proton, electron, and electron neutrino, or a sort of inverse decay of a proton into a neutron, electron, and electron neutrino with some antiparticles. Fermi also proposed that both these reactions find their explanation in a single term in the Hamiltonian of the very schematic form, which is 4 Fermi term, product of 4 fermions, no derivatives in the Lagrangian. Okay, we'll have more to say about this term. You've already heard more about this term as we proceed. Okay, now this beta decay process is not the only weak interaction process in the world. There are many others. One that was well studied by the middle of the last century was the process of the decay of pions. Pions decay primarily into muons and neutrinos. Now this looks like a very different process from these guys. See, this is a 4-particle process, whereas this here is a 3-particle process. Also, this process involves electrons, this process involves muons. You might think these completely different processes, what's the connection? However, we now know that these are actually very similar processes. I'm going to review for you why they're so similar in sort of modern language. The people studying their stuff then didn't know this, but in modern language, with a lot of inaccuracy, I'm going to tell you why these two things are similar. See, we know that there is some very rough sense in which a proton is 2 up quarks and a down quark, and a very rough sense in which a neutron is an up quark and 2 down quarks. In the same rough sense, a positive pion is an up quark and an anti-down quark. Now, in this very rough sense, what's really going on here, when a neutron goes to a proton or what's really going on here when a proton goes to a neutron, an electron, and a neutrino, is that what's happening is that this up quark here, which is one of these guys, transits into a down quark, making the neutron, plus the electron and the neutrino. So that transition process translates into the neutron going to the proton, electron, neutrino. Now, in a similar way, what's really going on when the pion decays is that this up quark goes into a down quark, which then annihilates with this anti-down quark. Okay? And giving rise to this muon and the neutrino. Okay? So, these two actually very similar processes. The decay of the proton and the decay of the pion are very similar. The big difference, of course, is that while this guy involves an electron, this guy involves a muon. But again, from our modern perspective of the weak interactions, we know that the electron and its neutrino, as far as weak interactions are concerned, are basically identical to the muon and its neutrino. The big difference between these particles is in their mass, which plays no role in the interactions. Okay, so though these processes look different, superficially look different, they're actually very similar processes. And while the modern understanding of these processes wasn't available, people had a sense they were similar processes. For instance, the coupling constant that entered these processes could be measured in both cases and had more or less the same value. So it was sort of clear that this was the same process going on. Now, as I mentioned before, Fermi had proposed that there was some sort of 4 Fermi interaction governing these processes. And then, if you wanted to get into details, the big question was, what was the precise nature of this 4 Fermi interaction? Now, if you've not thought about this kind of question before, you might think it's a strange question. If you have 4 bosons, let's say phi 1, phi 2, phi 3, phi 4, no derivatives in the Lagrangian, what do you mean, what is the 4 boson interaction? It's phi 1, phi 2, phi 3, phi 4. There's no question, that's what it is. The reason there's a question when we're talking about fermions is that fermions have spinor indices. Fermions are not by themselves scalars. However, a term in a Lagrangian has to be a scalar. Okay, so the spinor indices have to combine with each other in order to make scalars. And we can try, as a simple exercise in group theory, to classify all the ways in which this can be done. Okay, so let me start by considering a simple warm-up problem. Consider 4 different distinguishable representations of SU2. You know, the familiar thing that all of us have studied about quantum mechanics. Let these representations not be completely arbitrary, but be 2 J1s and 2 J2s. And for specificness, let J2 be less than J1. Question, how many ways are there of combining these 4 J's, J1, J1, J2, J2, into SU2 singlets? This is a simple question you could assign in your quantum mechanics course, and has a simple answer. One way of finding this answer is to proceed as follows. Take 1 J1 and 1 J2 and expand it into representations of SU2 by using Clebsch-Gordon rule. Okay? You get all the representations between J1 minus J2 up to J1 plus J2. And then you do the same thing with the other guy. You take J1 and J2 and you expand it into all the same guys. It's the same issue. Same issue. Okay, then what you have to do is to take one group of this, another group of this, and fuse them to get singlets. But of course, all of you know that the only time you get a spin 0 when you combine 2 SU2 representations is when J1 is equal to J2. Because otherwise you start with a spin that's not 0. So the only way you get singlets by fusing a line of this with an equal line of this is taking J1 minus J2 and combining with J1 minus J2. Similarly, J1 minus J2 plus 1 combining with J1 minus J2 plus 1 and so on. So for each of these fusion products here of the 2-particle state, there is exactly 1 singlet of the 4-particle state. Okay? Great. Now suppose we wanted to do the same thing for fermions. It's actually the same exercise in disguise. This is because, at least in Euclidean space, SO4, the Lorentz group of 4-dimensional space, is SU2 times SU2. So the exercise we worked out we can just use. A fermion is half 0 plus a 0 half. The second fermion is a half 0 plus a 0 half. And our rule was, fuse these guys in every way you can and combine equal representations. But the fusing we do SU2 by SU2. So for instance here, we get half goes to 0, 0. See, the half goes to 0, 0 plus 1. These go along for the ride. Or if you take this guy with this guy, okay, you'll get a half, and so on. Simple trivial exercise. This is the set of representations of SU2 times SU2 you get. And for every fusion product, you can combine with something else on the other side. Okay? Now, the counting of the number of singlets of group theory is a bit complicated by the fact that you have 2 scalars. For instance here, 2 vectors here, and the 2 components, the self-dual and the anti-self-dual part of the antisymmetric tensor. Now, whenever you've got multiplicities of a single representation, you can combine with that same representation on the other side in either way. You know, this vector could combine with either the corresponding this vector on the other side, or it could combine with that vector on the other side. So for the vectors, you get 4 singlets. Similarly, for the scalars, you get 4 singlets. The tensors, you get 2. Okay, so the total number of singlets in a combining for fermions is 10 singlets. Okay, so if you impose no other condition on the terms in your Lagrangian, there are 10 different singlet Lagrangian structures you can write down. If you put other constraints on your other constraints of the Lagrangian, you can cut down this number. Okay, now moving to the kind of language we heard about earlier. This combining is just a way of decomposing bilinears of fermions into representations. So you have the scalar and the second scalar, which is actually a pseudoscalar, it's a parity odd scalar. The vector and the second vector, which is a parity odd vector. And the tensor, I've not bothered to break up the tensor into self-dual and anti-self-dual parts, but both are there. Okay, so you can do this combining, for instance, we were studying beta decay in the neutron-proton sector. You can do the same combining in the electron-muon sector. Sorry, electron-neutrino sector. And then the Lagrangian is any one of these with the corresponding, for instance, this would be the SS prime, that 4-particle guy would be the SS prime Lagrangian. Okay, as I said, if you had no other constraints, there were 10 parameters in the possible set of Lagrangians you can write down. You may want to put other constraints, that's up to you. Okay, so this was the theoretical situation. Everyone knew this in the 40s and 50s. To specify the set of possible 4 Fermi interactions, we need to specify a bunch of parameters, 10 parameters. Okay. Now the question that some people started asking was, what are the precise values of these 10 parameters? And as was reviewed in the first talk today, there's the experimental situation was confusing. It appeared that beta decays were best explained by combinations of the S and the T, and maybe some pseudoscalar. Whereas it appeared that pion decays, and this was reviewed in detail, were best explained if you had an antisymmetric vector somewhere in the mix. Okay, the axial vector somewhere in the mix. In fact, if there was no P, but just an axial vector, people had already computed that would be the situation, that if there was a P in the mix, you would get decay primarily to electrons. If there was no P, but only an axial vector, it's a simple computation to show that muons would dominate over the creation of electrons by a factor of roughly 210 square. 210 being the ratio of the mass of the muon to the electron. Okay, so experimentalists eventually managed to find the subleading decay channel for the pion and found that this 210 squared was more or less right, giving near certain confidence that there was an axial vector in the game. However, though, the beta decays, as was already mentioned, appeared to favor other combinations, other values of these 10 parameters, what was going on. Okay, so now, now here comes George Sudarshan. In 1956, George Sudarshan was a young graduate student at Rockefeller. He enters the story. In the next few slides, I will describe his journey in his own words, using as far as possible direct quotes from Ananya Das Gupta's 2009 oral history interview of G. Sudarshan for TIFR archives. For the next 4 slides, I'm just going to be reading, okay? Okay, so in 1956, after he's written a couple of papers on other things, then his advisor Marshak says, "You like weak interactions? Why don't you look into them?" So Sudarshan does. The textbooks at that time, he said it was scalar or tensor. But if it was scalar or tensor, the decay of the pi meson of the muon and the neutrino should not take place anywhere near the rate at which it did. This we've already reviewed. This pi meson requires this axial vector. And this is somehow very important, I feel. And there was some consideration at that time about universal Fermi interactions. I got the idea that weak interactions must be the same. That there should be one law governing decay of pions and the other things. This is the hallmark of a good physicist, right? It's a mess. Forget it. Okay. One of the things to do was to look at the electron-neutrino angular correlations. Eventually, the great experimentalist we heard about, Madame Wu, and others started using gaseous targets so that everything was out in the open and one could determine it very well. So the question was, what was the interaction? I found all the claims of the scalar and the tensor were based on one experiment, on the angular correlation of helium-6 decay. They, the experimentalists, concluded that it was a tensor interaction because they found a positive angular correlation of small magnitude. So when I told Marshak that this could be wrong, he said, "Don't ever say it aloud. People will laugh at you if you say Madame Wu is wrong." But she was wrong. I said, as far as pi decay, I think he means by I said, I thought. As far as pi decay was concerned, it was very clear that it had to be either axial vector or pseudoscalar, as we've heard. Nothing else would work. So I went on the hunt to see why it should be by it, meaning also the beta decays might be governed by axial vector. I found that there was very little reason why it shouldn't be axial vector. I told Marshak that the axial vector seemed to be the universal one. This was just before the 1957 Rochester High Energy Conference. He said, look, you better be careful. If you say something like this and you're wrong, people will never look at your work and look again at your work. I said, that did not matter because I would be right. He replied, you have no reputation to lose, but I have a standing in the field. So the net result was that I didn't get the chance to present this 5 minutes would have made all the difference. You know, people often say he didn't present in this conference because he was a student. That's not the truth. As he says, the truth is Marshak didn't want to risk letting him present results that he thought might be ridiculous. That's the truth, in Sudarshan's own words. Okay. Marshak felt, this is my editorial comment, Marshak felt unsure of his students' results, I feel, and wanted them to be validated by an expert before going public. Returning to Sudarshan's words, Marshak suggested I have lunch with Murray Gell-Mann. Actually, he wanted me to be examined by Murray Gell-Mann. I told him in this matter I knew better than Gell-Mann, but Marshak was insistent. So I presented every possible argument to Gell-Mann in great detail, almost like a leaked brief. Gell-Mann was very impressed. Marshak asked, so what do you think of George's work? Gell-Mann said, first class, I think this is finally the solution. Now, of course, these are Sudarshan's own words. We don't have too much independent corroboration, but for what it's worth. Then I was told by Marshak to write the thing up. I did, and I gave him the write-up the next morning. He didn't do a thing with it for 2 months. This was his mistake, his error in judgment. He simply thought that this was not very important. He was busy with other things, so it never got sent to the journal. Marshak presented, now this is my editorial commenting, Marshak presented this paper in a conference a few months later. We heard about it, this Venice Padua conference. Before the conference proceedings were published, Feynman and Gell-Mann published a competing paper with the same results. For a while, Sudarshan and Marshak's unpublished work was relatively unknown, and it took decades for the actual sequence of publication to seep into the community's consciousness, which of course is what it is. Fine. Now, last 2 slides. This, yes, good, last 2 minutes. This talk is officially titled ECG Through the Eyes of the Younger Generation. Feels strange for me to be called young, but okay. Younger is probably right. Okay. The title emboldens me to give you my personal assessment of the importance of Sudarshan's work. Okay. For a while in the early 1950s, the problem I feel, this is my editorial commenting, last 2 slides, okay. For a while in the early 1950s, the problem of weak interactions must have seemed like a matter of grungy detail. You know, Fermi's done the great stuff. He's found it's 4 Fermi interactions, he gets most things right, details are left to be filled up. What are these 10 parameters? Maybe people would have said, who really cares? Okay. All that remained was to find the actual values of the parameters. Some people might reasonably have felt that the precise values of parameters, while of course important to get straight because we need to know everything about reality, were unlikely to teach you anything of deep conceptual significance. I suspect Marshak took this view. Now, a modern-day analogy for such a scenario might be the determination of the precise values of all the Yukawa parameters of the standard model. It's clearly important to get them all right because that's how reality is. But what exactly would have, had the top mass been 5 GeV heavier or less heavy? It's not like we would have had a conceptual dissonance with the standard model. Sudarshan, on the other hand, appeared to be driven by the hope that the precise form of the 4 Fermi interaction would turn out to be simple, universal, and beautiful. And he was correct. Oops. And I've said it twice. Now, other people also were involved in discovering B minus A, including Gell-Mann and Feynman. And this is what Feynman had to say about the beauty and thrill of his own discovery. As I thought about it, he says, recalling his discovery, I beheld it in my mind's eye. The goddamn thing was shining. Now, it was not as beautiful as Dirac's or Maxwell's, but my equation for beta decay was a bit like that. Okay? So, of course, it was a beautiful, beautiful thing, not some messy set of random vector in a space of 10 parameters. It's a beautiful, universal, symmetrical structure. Okay. Now, in my opinion, the discovery of V minus A made the subsequent developments in the standard model almost inevitable. Why do I say that? Not because of detail, but just because it made it clear that there was something simple and beautiful out there to uncover. And once that's clear, people will uncover it. Okay? So it proved the vectorial nature and the universality of the 4 Fermi interactions were the key to uncovering the SUT gauge structure of weak interactions. because it's the SU2 gauge bosons that couple to these currents. The V minus A rather than V nature of the interactions was key to uncover the chiral nature of the standard model. The fact that only chirality for positive chirality fermions are charged under the weak SU2. For this reason, I feel, dressing up, making it correct, filling out details has a great role in physics. But the first real indication that there's something simple, beautiful, that I have to find out there is perhaps one of the most important elements in scientific discovery. And in my opinion, this V minus A business was that moment for the standard model, or at least was partly that. And so in my opinion, V minus A was one of the great scientific accomplishments of the previous century. Nobel, not Nobel, notwithstanding. Mahatma Gandhi was never given a Nobel. I mean, it doesn't say anything about the Mahatma Gandhi, it says something about the Nobel. Okay. We can all be very proud of that this discovery was made in the large part by a young Indian who grew up in a small town in Kerala, a student of Madras Christian College, and then at TIFR, just a couple of years out of India. Okay, thank you.